Radioactivity. By the end of this lesson, you should be able to state what radioactivity is, name common detectors for radioactive emissions. The nucleus of an atom is very, very small. The size of a nucleus is of the order of 10 to the power of negative 15 meters compared to the atom, which is of the order of 10 to the power of negative 10 meters. Imagine that the nucleus is a rice grain, which is about 1 millimeter thick, and the atom is as big as a football field. It would take 100,000 rice grains to fill up the 100-meter length of the football field. The nucleus takes up a very, very small space in the center of the atom. Why? Nucleons, which are made up of protons and neutrons in the nucleus, are held or bound together by a powerful attractive force called the strong nuclear force, or strong force. This force acts only when the nucleons are very near each other. Thus, the nucleons are held very close to each other, and hence the nucleus occupies a very small space. The nucleus is made up of protons and neutrons. Protons and neutrons are called nucleons. When two protons are brought close to each other, what kind of force will the protons experience? The protons are of the same charge. Thus, when they are brought near to each other, they will experience a repulsive force. The repulsive force will tend to push the protons away from each other. Then how come the protons in a nucleus do not move apart due to this repulsive force? There is another force that acts on the nucleons. The force is called strong force. The strong force holds the nucleons together. It is a short-ranged force because it only acts on the nucleons that are very close to each other. The strong force holds together 1. Protons, 2. Neutrons, and 3. Protons and neutrons. When two protons are close to each other, they experience a repulsive force that pushes them apart. At the same time, the strong force also acts on the protons when they are very close to each other. The strong force is greater than the repulsive force. Thus, this force binds the neutrons and the protons together. Identify the number of protons and neutrons in the nuclei shown. Elements with small nuclei have protons and neutrons very close to each other. Hence, the short-ranged, strong force can easily overcome the repulsive force between the protons. Thus, the nucleus is stable. However, nuclei of heavy elements, which have a large number of protons and neutrons, are unstable. Why? The strong force only binds side-by-side protons, like protons A and B. The larger the distance between the protons, the weaker is the strong force. The repulsive force between protons acts over a long range. It will exist between many pairs of protons, like A and B, A and C, and even B and C. Hence, for protons which are far apart, like those on opposite edges of a large nucleus, the force that binds the two protons is weak compared to the repulsive force. Thus, the larger nucleus is less stable than the smaller nucleus. Radioactivity is the spontaneous splitting or disintegration of an unstable nucleus with the emission of particles or energy to become stable. This process is also known as radioactive decay. There are three types of radioactive emissions. 1. Alpha particle, 2. Beta particle, and 3. Gamma rays. Click on each radioactive emission to find out more about the decays. In an alpha decay, the nucleus emits an alpha particle. An alpha particle is a helium nucleus made up of 2 protons and 2 neutrons. In a beta decay, the nucleus emits a beta particle. A beta particle is a fast-moving electron. In gamma decay, the nucleus emits gamma rays. Gamma rays are high-frequency electromagnetic waves. The Geiger-Müller tube, or GM tube, is one of the common detectors of radioactivity. It can detect alpha and beta particles and gamma rays. How does the GM tube work? The GM tube works by using the ionizing effect of radioactivity. Alpha particles which ionize strongly are easiest to be detected with a GM tube. The GM tube is filled with argon gas at low pressure. A positive voltage of about 450 volts is applied to a thin central wire in the tube, which thus acts as the anode. The negative potential is applied to the tube, thus making the tube the cathode. When a radioactive particle enters the tube, it will ionize the argon atom by knocking out an electron. The electron is then accelerated to the central wire, anode, knocking electrons from other argon atoms in its path. This results in many electrons being accelerated to the anode. Thus, one single particle can cause many electrons to be accelerated to the anode, producing a pulse of current which can be amplified and counted. The pulses of current are counted by a counter or rate meter. The counter or rate meter indicates the activity of the radioactive source by giving the count rate in counts per second or counts per minute. Click the labels to see the functions of each part of the Geiger-Müller tube. Radioactivity was accidentally discovered in 1896 by a French scientist, Antoine-Henri Becquerel. He discovered that uranium compounds, later determined as radioactive, would expose or darken a photographic film, even when the film was wrapped up so that light could not get in. This effect of darkening of the photographic film can be used to measure how much radiation has struck the film. Nuclear industry workers wear film badges. The badges have windows made of different materials that stop different types of emissions. The windows may be made of lead and aluminium. The thin lead window stops alpha and beta particles. Gamma rays will expose the film behind it. If no gamma rays are present, the film is not exposed. The thin aluminium window will stop alpha particles. Beta particles and gamma rays will expose the film behind it. The film at the topmost window is exposed to all three radiations. All the radiations expose the film in the same way. By comparing the amount of exposure on the film behind each window, the amount of the radiation due to alpha particles, beta particles, or gamma rays can be determined. Film badges are sent to the laboratory to be developed like photographs each month. The exposure of each worker to the various radiations can be determined. The track patterns of the different radioactive radiations can be observed by using a cloud chamber. The cloud chamber may be rectangular or round. The chamber comprises 1. A clear plastic box, 2. Felt, 3. A black metal plate at the bottom of the chamber, and 4. Dry ice. Click the labels to see the function of each part of the cloud chamber. Dry ice is placed under the black metal plate at the bottom of the chamber. This is to ensure that the bottom of the chamber is very cold, while the top is kept at room temperature. The upper portion of the cloud chamber is lined with felt that has been soaked in alcohol. The room temperature in the upper portion of the chamber causes the alcohol to vaporize. The high concentration of alcohol vapor at the top region causes the vapor to diffuse downwards. What can you say about the vapor that has diffused downwards? The low temperature at the bottom causes the vapor that is diffused downwards to be supercooled. The vapor is at a temperature at which it readily condenses into liquid. What happens when a radioactive source is put into the chamber? Radioactive rays from the source ionize the atoms in the vapor. Other nearby vapor atoms are attracted to these ionized atoms and condense on them. This will cause misty tracks to form along the path that the radioactive ray took through the chamber. The black metal plate at the bottom of the chamber helps to make these tracks more visible. What can you say about the tracks of the different types of radioactive emissions? Alpha radiation produces thick, straight tracks. The tracks are thick because of their high ionizing ability. Straight tracks are due to their large mass, making alpha particles difficult to deflect. Beta radiation produces thin, twisted tracks. The thin, twisted tracks are due to the weak ionizing ability of the beta particle. Twisted tracks are due to their small mass, making beta particles easier to deflect. Gamma radiation produces short, thin, and scattered tracks. This is due to the extremely weak ionizing ability of gamma rays. The track patterns formed in cloud chambers can be used to differentiate between alpha, beta, and gamma radiations. The spark counter is an instrument that uses the ionizing effect of radioactivity. For this reason, the spark counter is normally used to detect alpha particles. The spark counter is made up of wire gauze and a single thin wire. The wire gauze is connected to the negative voltage of about 450 volts, making it the cathode. The thin wire connected to the positive voltage functions as the anode. How does the spark counter work? The voltage between the gauze and the wire is then adjusted until it is just below the voltage required to produce sparks. When a radioactive source which produces alpha between the gauze and the wire is ionized by it, the negative ions are accelerated to the wire, anode, knocking the electrons from other air molecules in its path. This results in many electrons being accelerated to the anode. A pulse of current will then be produced. The pulses of current are counted by a counter or rate meter. The counter or rate meter indicates the activity of the radioactive source by giving the count rate in counts per second or counts per minute. The electroscope is another radioactive detector. How does an electroscope work? An electroscope is charged up by rubbing the metal disc with a piece of dry cloth. When an electroscope is charged, the gold leaf is deflected because the charges on the gold leaf repel the charges on the metal stalk. Dry air is a good charge insulator. A charged electroscope will stay that way unless it discharges through the metal disc. What happens when a radioactive source is brought near the disc? When a radioactive source is brought near the metal disc, the air around the metal plate is ionized. The electroscope discharges, and the gold leaf falls. Click on any box of the crossword and key in the answer.